everyone. I am Ahmed Ismail, metric number 231149. Today I'll be presenting my findings from the first assignment for Fluid Mechanics 1 under the guidance of Dr. Nuruddin. The code subject is EMM3316. In this presentation, I'll be explaining how three important fluid properties, viscosity, density, and surface tension, affect engineering design and operation. These properties play a vital role in fluid flow, equipment design, and overall engineering efficiency. So, for the introduction, fluids are everywhere in engineering, in pipelines, pumps, reactors, and even heat exchangers. To design and operate equipment reliably, we must understand how fluids behave. Today, I'll focus on three fluid properties: viscosity, a fluid resistance to flow or thickness; density, the fluid mass per unit volume; surface tension, the force that acts at the surface of a fluid. And each of these influences how fluid behaves in engineering applications. Let's briefly define them and understand their engineering significance. So first of all, I'll go through the definition and importance. So viscosity is the measure of a fluid's internal resistance to flow. The higher the viscosity, the harder it is to pump it. It's highly temperature dependent. For example, oil becomes less viscous when heated. And then for density. Density is the fluid's mass per unit volume. Density affects pressure distribution and separation. It's why equipment like hydrocyclones can separate liquids of different densities. Now, finally, for surface tension, this is the force that causes a fluid surface to minimize its area. Surface tension affects droplet behavior, coating, and emulsion formation, making it vital for microfluids and spraying applications. Now, for the engineering applications, each of these properties impacts engineering design. Viscosity in pipelines determines how much pumping energy is required in transporting viscous liquids like crude oil. High viscosity means higher pressure losses and stronger pumps. Density in separation and mixing enables equipment like centrifuges to separate fluid phases effectively. Surface tension in equipment design influence droplet formation and capillarity, critical in microfluids and coating applications. Now, for the case study, a common challenge occurs when transporting mixtures like oil, water, and gas. Here are some. Lower viscosity fluids reduce pumping costs, but density differences can cause uh, stratification or slugging. Surface tension can cause droplets to coalesce, leading to unsteady flow. Engineering solutions to this challenge include adding emulsifiers or surfactants to reduce surface tensions, adjusting pipeline design to maintain better flow, maintaining optimal temperature, and using flow conditioners to control flow behavior. And here is the summary table. We can see viscosity and its definition and its key engineering effect and its example application. So for viscosity, it's resistance to flow, increase pumping energy and guides turbulence control, and pipeline design, heat exchanger for the example. And then for density, the definition is mass per unit volume. It affects separation and pressure head, and an example of it is hydrocyclones, multi-phase pipelines. And finally, for surface tensions, cohesive force at fluid surface controls droplet formation, capillarity, and mixing, spraying, microfluids, flow stability. Now, finally, for the conclusion, understanding fluid properties, viscosity, density, and surface tension is critical for tackling engineering design and operational challenges. These properties do not work in isolation. Their interplay can define the success of equipment design and fluid processing. With the right theoretical knowledge and engineering judgment, we can optimize equipment, reduce energy usage, and design safer and more sustainable systems. Thank you for listening. That's it for me.